Thank you very much for attending this webinar. I'd like to thank Frantic and Kema for inviting me to deliver this presentation, and also I'd like to thank Evgeny, who has been helping me to prepare this presentation. Now, the title of this seminar is the Coupled Inductors in Multiphase Boost Converters. And here is a short outline here. We're going to talk about fundamentals of coupled inductors and transformers, interleaved boost, interleaved coupled inductor structure, and then, which I think is a highlight here, combined circuit and magnetic simulation. And throughout this presentation, I'm going to talk a little bit about elements of the magnetic design of a coupled inductor, but obviously due to the shortage of time and the time limit, I'll not be able to go deeply into it. Now, as Kema said, we're going to have a question and answer session following the presentation, and there'll be ample time for questions. So let me start off with the question, what is a coupled inductor? We have windings that are sort of coupled in the sense that a flux from one winding is going into the other winding, and then some of the flux escapes, and this is the leakage inductance. Now, what is the difference between coupled inductors and transformer? The difference in the application, not in the structure. They could look the same. The point is that coupled inductors are storing energy. That is, you can have energy coming in one side and also coming in from the other side, same time. On the other hand, when we are talking about transformer, what we mean is that we have an element in which the input power is going out at the same instant to the output, so there's no storage here. So the element here is transparent to the power. So this is the main difference. Now, very quickly, I'll go over the modeling of a coupled inductor. This is the physics of coupled inductor, these two equations. And what they are saying is that we have an inductor, and then we have some flux, the mutual inductance, which represent the flux coming from the other side. And same thing goes for the other output. And we can translate it into an equivalent circuit that looks something like that. When this is a dependent voltage source, and the value here is this M, the mutual inductance, times the current here, and this is vice versa to the other side. For a given frequency, we can use the phasor analysis, and in this case, the derivative becomes omega M, derivative of the I, if it's cosine omega t, and then we end up with this very familiar equivalent circuit or model of a coupled inductor, where M is equal to the coupling coefficient, which is the ratio of the flux going from one to the other side, square root of L1 and L2, and in fact, the way to measure the coupling coefficient is to measure the mutual inductance, and then to get the value here from M over square root of L1, L2. Another way to represent transformers, coupled inductors, is in the engineering domain, I would say, and this is this equivalent circuit for a transformer with leakage. So this could be either a coupled inductor or a transformer. In the coupled inductor, you may have different leakages, but this is an electrical representation. It's not a magnetic representation. I'm going to talk about it a little bit later. In this case, we see here the leakage, we see the magnetization inductance, and for the transfer ratio, we have an ideal transformer, which good coupling, K equal to 1, for the voltage ratio. So this is the very basic, which I think most of you, if not all of you, are very familiar with. So let me go now into the issue of interleaved multiphase converters. Now, in this case, we are talking about, in this presentation, about a boost converter. We have two transistors, two inductors, and they are working together. Now, boosts are used for step-up voltage. Power factor correction will typically contain a boost one way or the other. Now, why would we like to have two inductors, two transistors? Well, first of all, it's the issue of power sharing. Like if the power is high, you would not like to have one inductor, one transistor. You rather distribute the power among various inductors. Also helps to dissipate the power or better thermal conduction. So it is a practice in the power electronics that when you go to higher and higher power to work in parallel. But here, not only that we have two units, we operate them in a interleaved way. That is, we are not operating them together. There is a delay between one and the other. In the case of two units, it's 180 degrees. And this helps to sort of cancel partially or more or less the ripple. So here I'm showing a simulation of a system like that. Here are the gate drive. This is for duty cycle of 0.5. These are the gate drive. It's about 50% due to the rise and fall time. It's not exactly 50%. But what we see here very clearly that the ripple are in opposite direction, because when one is working, the other one is not. The diode is working, so that we have an opposite polarity of the ripple. So when they are combined at the input, like here, then there is a cancellation here. Here, because it's not exactly 0.5, it's not zero, but it's small ripple. Very important in a boost converter is the ripple at the output, usually very high because of the pulsing here. And also here we have an improvement due to the higher frequency, you might say. So it is improving the ripple, and this is one way to operate a multi-phase boost converter. If the duty cycle deviates from 0.5, like 0.8 or 0.2 or 3, then the cancellation is not very good. You see that the inductor current is sort of shifted because of the pulses, the way they are driving the transistors, and then we get a much higher ripple. Still, there is some cancellation, some improvements, but it's not as in the case of 0.5, but still it is better than just a single inductor. Now comes the idea of coupled inductors. The idea is that rather than having two separate inductors, we're going to use inductors which are coupled. And in this case, I'm showing here coupling the same direction. The dots are here. There is another way to do it, alternative way, in which there is a reverse direction of connection. Let me just say that this is better. But I'm showing this just for the sake of then comparing the two and understanding later on why this reverse connection better, okay? So this is like a reference, you might say. So what we have here is that we have two inductors which are wound on the same body, and so they are coupled with a certain coupling coefficient, and the aim here is to have a smaller size, smaller footprint. Obviously, it's smaller if it's one unit and a smaller size, then it'll be a lower cost. And if it is the same size, then perhaps we can get, or surely we can get better performance. So the idea of coupling is really saving in the operation. Overall, it is like an interleaved multi-phase converter, but the magnetics is, I'd say, smart magnetics that we have it in a coupled arrangement. Just to get a first impression of what is going on, I've replaced the coupled inductor with the transformer equivalent circuit. These are obviously not coupled, okay? There are dots here which I erased, and this is because of LT Spice putting the dots on the inductor, but they are not coupled here, okay? So this is like an equivalent circuit of a coupled inductor or a transformer, you might say, with the leakage, and in the transformer way of looking at it, rather than mutual inductance, okay? So what we see is the following. If K, the coupling coefficient, is 0, no coupling, then we end up with two inductors. This is the regular case. If K is approaching 1, then we are going to have here actually a transformer, very well coupled. And in fact, here you're going to have a short between these two. So K has to be somewhere in between. And this sort of already shows that this is not a simple thing to design, because there are many, many degrees of freedom here, the value here, the coupling, and the ripple. So this is the problem with actually designing a unit like this, and I hope that this presentation will kind of help those who are interested in actually understanding better the design of a coupled inductor. So to better understand what is going on, I have here now, side by side, two cases. This is a boost interleaved, not coupled. There's no coupling here. The dots, again, are just the LT spice notation. There's graphics, and it does not indicate coupling. The coupling is indicated by this directive. Here is coupling between L1 and L2 with a coupling coefficient. This is a parameter of, in this case, 0.5. Okay? So I'm running these side by side just to see the difference between them and how they behave. Now, as it turns out, to get the same ripple in the inductor here and here, and this would be my target, to have the same ripple in the two cases, I can define a different target, but this is what I'm defining here. Then it turns out the inductance that I need here is larger than the original uncoupled case. Okay, so this is this coefficient of how much larger is this inductor than this one. And here is a run in which I've already tuned the two to have the same ripple in the inductor. So 1 is the coupled and 1 or 11 is the uncoupled. And here you see that the ripple is the same. This is for 0.3 duty cycle, coupling coefficient of 0.5, and it turns out to get this, you need that the inductance of the coupled inductors of each winding will be twice that of the uncoupled. So you lose here, and of course then you have to do the summation of losing here, gaining there, and see how much did you actually gain net in this case. This is for 0.3, and for duty cycle of 0.6, again, the target here is to have the same ripple. This is for the same coupling coefficient, same size factor, and you see that the two are in the output the same ripple. At the input, there is some advantage to the coupled already. You see the green is the one is the coupled, and the ripple at the input is a bit, actually almost half that of the output. So of course I could have decided that I want these ripples to be the same, and this will of course change the situation, and then these ripples will not be exactly the same. Okay, so this is something I can play with. So as I've said, there are two ways to do it. There is the direct connection, same polarity, or reverse polarity. And here now is the reverse polarity. Here are the dots. Everything is the same. This is again the reference, 50 microhenry, two separate inductors compared to this coupled inductor. And here it is. What I see here, again, for a duty cycle of 0.3, coupling coefficient of 0.5, you see that I need only 1.25 larger inductance than in the case of the same polarity of the dots. Okay, this reverse case, I can get the same performance in terms of the same ripple with a much smaller inductance. Again, this does not say, this is not one-to-one corresponding to the size, because the size also depends on the flux, which I'm going to talk about. And it's not just the current and the ripple, you have to worry about other things. But you see that on in all, on this comparison, there is a very important difference between the two cases, and the size of the inductance, the value could be much lower than in the case of the same polarity. Okay. Also, we see that the behavior is different, and I'll talk about it a little bit later. Point 6, duty cycle, same story, nothing is changing. In this case, by the way, the ripple at the input is the same for the two cases, and the output also the same thing. Again, due to the interleaving, there is a advantage over one single inductor, of course. So overall, there is an improvement here, and this is just 1 point here. So if I sort of compare the two, I see that for different coupling coefficient, I was working here, I was demonstrating it for the 0.5, I get different values of inductance that I need in the coupled inductor. Now again, it has to do with what is my target optimum and what I'm looking for, if it is the ripple at the input of the inductor. And again, this is part of the information that is needed, because again, this doesn't say immediately how large will be the element and how exactly I'm going to design it. Now to the question of the shape, which is kind of very interesting, I think. We've seen that in the case of the reverse polarity of the inductors, we have a waveform for the ripple that looks like this. Now this means that in this portion, for the same inductance, the voltage imposed is much lower, because the slope is depending on the voltage imposed on the inductor. And we see here that it's almost straight line, while this is not the case here. The question is, why is this so? So let me try to explain it in an intuitive way. You can write tens, if not hundreds of equations here, and then get another equation that you have to solve. And let me try to explain it so that we understand what is really going on here in an intuitive way. So what I did here, I've looked at one particular point, which is the important one. This is actually this section here, in which one transistor is shorted, and here on the other side, the diode is conducting. And these are just arbitrary numbers, just for demonstration. I'm assuming 24 volt at the input and 54 volt at the output. Okay, so the first thing to notice is that we have a voltage drop on these inductors, of course, the difference, and the polarity coincide the same thing for the two inductors. Plus is here and plus is here. And this is in the case of the reverse direction, because the voltages are reversed. And I can represent it as a transformer. Well, this is not a optimum transformer, it's an inductor, it has a lot of inductance, but it is operating as a transformer also. So what we see here is a transformer that on the one side has 30 volt, this is this difference here, on the other side has 24 volt. If the voltages would have been exactly the same, nothing would have happened, because it's all balanced. But since we have 24 volts, then we have 6 volt on the leakage inductance, which generate a certain ripple and with a certain slope corresponding to the 6 volt. Now, in the case of the same direction, what we find that now we have a reverse voltage on this winding here. So the difference is the sum here of 30 plus 24, 54. So this is this slope here. And it will be large, while in the case of the point that I'm showing here, when we have the coupled inductor, when one transistor is conducting and the other one is not, then we have this slope. For this case, when the two diodes are conducting, this will be duty cycle, say, smaller than 0.5, then you have a larger voltage and this is why you have a larger slope here. So this slope is really obtained by this reverse direction, and this is why we prefer this. So now comes the question, how do we get large leakage inductance that we need here? Well, there are two ways to go. One is to sort of separate the windings, and then the distance here, the longer the distance, then the larger will be the leakage inductance, because you have more room for this flux to escape, you might say. And there is actually a nice equation that you can predict the amount of leakage in this case. Or you can put the windings apart, and this again will increase the leakage because you have more flux escaping here, or side by side also. But all these bring about a fairly small amount of leakage, that if the coupling coefficient is still fairly high, and here we like to have a small coupling coefficient, a large leakage. And the way to do it is to have a bypass, okay? So we have a structure like this. It can take various configuration or alternative way of doing it. You can have the same gap, you can have different gaps, one small, you can have no gap. Anyhow, the idea is the following. You have one winding, another winding, and then you have a bypass with a small reluctance. I'll talk about it in a second. And by this, more flux is escaping and less flux is getting to the other side. And the coupling coefficient is the ratio between the flux that eventually entered L2 divided by the original flux. So the more flux is, the larger is phi sub 2, the smaller will be the coupling coefficient, and you can adjust it by the gap here and here. And so this is one way to go, and this is a very good way to do that. So now we need some way of understanding or quantizing the magnetic parameter, okay? The simulation that I showed is in pure electrical. We don't have any notion what is the flux, what is the magnetic flux density, MMF. We don't have any information in this domain, in the domain of the electrical simulation. For that, we need another tool, and this could be very handy, the magnetic reluctance equivalent circuit. And again, I'm sure that most of you know about it and are familiar, if not all of you, but let me go over it very quickly. If I have here say a rod of ferrite with a gap, then the reluctance is defined as the length of the piece, and here is the total ferrite, L1 plus L2, divided by the permeability, total permeability, times the cross-section area. For the gap, the same thing, except the permeability is much smaller because the relative permeability of air is 1. So this number is usually much smaller because of this large number. In ferrite, 2,003, 4,000 even. And therefore, the reluctance is primarily controlled by the gap if it's not very, very small. So using this concept, we can build an equivalent circuit. It is an electrical circuit, but it is mimicking or emulating the magnetic part. And we see here the three reluctances of this body, three reluctances. And now we need an interface between the electrical and the magnetic part. And this is done by these dependent sources. Like this dependent source is n, the number of turns, times ddt is the operator of L5 for derivative. So this is the derivative of the current here. The current represents here the flux, okay? Flux is emulated by current. The reluctance is emulated by resistance. And the MMF is voltage. So by taking the derivative of the current here, I get the back EMF, And so this is the interface, the electrical interface between the electrical part and the magnetic part. So this is very handy. Again, this now gives us information about things like what is the flux in this arm, which is very important in the design consideration. And now I understand that the coupling coefficient can be very easily derived from here, because if I have a flux coming in from this winding, and then it goes this way, and the flux is emulated by a current, then I'm talking about a current divider, okay? And the question is how much of it is going on to the other winding, and this is like a current divider, and by this I can understand what should be the reluctances to get a given coupling coefficient. Now that we have the two tools, we can combine them. So rather than having here an inductor, or coupled inductor, I should say, I have this structure, which represents the magnetic part of the coupled inductor, plus the two terminals, which are representing the inductor. So these are connected here, okay? These points are connected by this node, and by the name, by the designation here, and L22 and N2 is here. And we can run this together and get both the electrical information and the magnetic information at the same time, which is very, very important. And here it is. This is for a duty cycle which is larger than 0.5. You see the overlapping of the gates. And what I'm showing here is the current here when it is run with this reluctance model, and when it is run with the regular inductor, okay? And this is for the reluctance case, and this is for the regular inductor, coupled inductor, and you see that if it is done correctly, it's exactly the same. So now you can ask, okay, if the same, why do I need it? I need it because if I run it now like this, I can get information which are not available in the electrical domain, like the flux. For example, I can see what is the flux in a given part of this structure. And if I know what is the flux, flux is related to magnetic flux density times the area, or magnetic flux density is flux over area. So therefore, if I know the flux, I can, for example, just an example, select the cross-section area that I need, okay? So this is very, very important information in, first of all, understanding what is going on, the losses and the other aspect, and also for the design. And finally, let me say a word about the current sharing. Is there a need for current sharing in this case? Well, you would have thought that since it is coupled, then there is no need, because if it's coupled, then it will sort of divide equally the current, but not so. The coupled effect is on AC only, depends on the IDT, on the derivative of the current. So as far as the DC goes, there's no coupling here. So again, we have a DC circuit, the input, parasitic resistance. This is the parasitic resistance of the inductor, of the transistor. And then we have an average voltage here and here, which is the duty cycle times the output voltage. I'm neglecting the voltage drop of the diode. So if this is not absolutely balanced, everything is the same, like the resistors and the duty cycle, the current will not be the same, the DC current. And so you definitely need current control, current sharing control in this case. If you want the current to be exactly the same, you may tolerate some deviation, and then of course you may skip it, but a good practice is to have a control current share. So what did we see here? I very quickly went over the fundamentals of coupled inductors. They talked about direct and inverse coupling. And what is very important, in my opinion, is the combination of circuit and reluctance simulation that give you a lot of information. Now, I didn't go into very fine details of the design, and so there is something to do next time. So this brings me to the end here. Thank you very much for your attention. I hope you found it of interest. And as we've said, if you have questions, please write them at the chat part, and I'll try to answer as much as I can.